Now, what I want to show you is that exponentials are orthogonal bases for the representation of signals. Now we will talk about particularly complex exponentials where the amplitude is constant. So we're talking about exponentials of this class, j omega t. We have sigma equals 0. So in the complex plane, we're here. We're over this axis where sigma equals 0. And then we will come back to the discrete case. We'll be talking about exponentials where the radius is 1. So we have 1 times the angle. So we will be real part of omega, very ugly omega, imaginary part of omega, will be right in the unit circle, right here, over the unit circle. We'll be talking about these guys. Let's start with this one. Let me check my notes to make sure I'm not missing anything. What I want to show you is that the family of exponentials of this kind is a orthogonal basis for any periodical signal. What does it mean to be an orthogonal basis? Say I have a basis composed of vectors b1, b2, b3. I can form the matrix B, which is vector b1 in the first column, vector b2 in the second column, vector b3 in the third column. If this is a basis for C3, so we're working with 3 dimensions, so each of these vectors have 3 entries. If this is a basis for the C3 space, then we can represent any vector v belonging to C3 as v equals some constant, complex constant, a1 times vector b1 plus a2 times vector b2 plus a3 times vector b3, right? If this is a basis, then this representation is possible. if this is an orthogonal basis, meaning that by, vector bi, dot product, inner product with vector bj equals 0, this is Hermitian, which is transposed and complex conjugate, which is the generalization of transpose for complex number when we do inner products. So if I do the inner products of each pair with I different of j, if I get 0 for every inner product, that means this basis is orthogonal. If it is orthogonal, there's a unique representation. There's a unique set of constants A1, A2, A3, right? If it's not orthogonal, there might be some possibilities of A1, A2, A3. So I can find it with the pseudo-inverse matrix. But if they're orthogonal, it's easy to find A1, A2, A3. How can I do it? I have some vector v, which is a linear combination of these 3 vectors. Now I want to know which is the value of A1. I know v, and I know the 3 of them. I want to know this.
Well, you can solve the linear system of equations.
I can solve the linear system of equations, even if this is not orthogonal. If this is orthogonal, I don't need to solve a linear system of equations. I can find only this, or only this, or only this independently. How can I find the projection of V over B1? Inner product. A1 equals this, B1 V, which is B1 Hermitian times V. Same for A2, same for A3. Actually, this is true when B1, B2, and B3 are normal vectors, when they are versors. If they're not normal, I still have to divide by something here, right? To the length, how do I call it in English? The norm of the vector. The length, the norm or norm squared. I have to check it. So if they are orthogonal, I have to do this and divide by the norm or norm squared. If they orthonormal, they're normalized. If their norm is 1, then I do just this. So the advantage of being orthogonal is that I don't need to solve a linear system. I can find all the coefficients independently. In 2 weeks, we'll be studying Fourier series and Fourier transforms. And we will see that any periodical signal x of t with a period t o can be decomposed, can be represented as exponentials with this same period. So with omega 0 times n t. What is this n? It's so this implies omega 0 equals 2 pi over period. So I have the fundamental frequency, then 2 times it, then 3 times, 4 times, 5 times, 0 times, which is e to the j0 is constant, minus 1, minus 2 as well, because I have the positive and the negative exponentials. Each of them will be multiplied by some coefficient dn, and I want to find dn. I want to take my periodic signal, for instance, a Sol wave. So T0 is here. I want to represent it in this way. What I have to do is to find every dn. How can I do it? If these vectors, if these signals, e to the j omega t, e to the j 2 omega t, e to the j 3 omega t are orthogonal among themselves, then I can do just an inner product of them to find dn. What is an inner product of continuous functions? Well, what is an inner product of some two vectors that belong to C3? Say we have U and V. They belong to C3. The inner product is this, right? Hermitian V. What does this mean? The inner product returns a scalar or a vector? A scalar. This scalar is sum n from n, yes, n from 1 to 3. U index n Hermitian, so it's complex conjugate. V n. So inner product between two complex vectors with 3 entries here is this. You multiply element-wise. If it is complex, you have to multiply with complex conjugate in one of them. And the result is the value of your inner product. So how can we extend that to continuous functions? Now let's define the inner product of x of t, y of t. Here I have a sum element-wise. What is a sum element-wise when I'm in a continuous space?
An integration.
Integration. So I have to multiply them, x of t, y of t. It's the Hermitian complex conjugate. So let's do the complex conjugate of one of them if they're complex. sum of the product. So integral of the product, dt. Now I'm talking about the space of periodical functions with period t0. So I have to integrate across one full period. I can go from 0 to t0 or plus anything I want here, plus a. I just have to integrate over one whole period. I can simplify this notation. I can do this. T. This is not a limit of integration. This is indicating that I'm doing the integral over one whole period. And I want to show you now that if we take two complex exponentials with different values for n, they're orthogonal. So, for instance, where can let's erase this. First, let's do the algebra, then we do the graph. Let's do the inner product between e to the j omega 0 and 3 t. So it's 3 times the fundamental frequency of some arbitrary signal, and j omega 0 2 t. That's the definition of inner product. I will integrate over a whole period. Let's go from 0 to t0 to begin. E to the j omega 0 3 t. This guy has to be complex conjugate. What's the complex conjugate of this number? I just have to shift the sign of the imaginary part or of the angle. This guy is just angle. If I do this, I'm shifting the sign of the angle. So this is the complex conjugate of this guy. J omega 0 to t dt. We have our inner product as e to the j omega 0 minus 3 plus 2 minus 1 t dt. I am integrating over a whole period. In this case, I got the fundamental frequency, minus 3 plus 2. If I had minus 4, I would get minus 2 times the fundamental frequency. Let's see what happens here. What happens if I integrate this guy over one whole period? The real part is a cosine. A cosine behaves like this. This is one period of a cosine. I integrate it, I get 0, right? The imaginary part is a sine. This is a sine. I integrate it, I get 0. If I had 10 and 2, and I would have minus 10 plus 2 would be minus 8. I would be integrating over 8 periods, always an integer number of periods. So if I integrate over an integer number of periods, I always get 0. Now let's go to the graphs and see that this is true for any phase, any period, any shift I give over the integration interval. Complex exponentials. Orthogonal. Close all tabs. This script shows empirically that sinusoids with different frequencies, but they're integer multiples of a fundamental frequency, are orthogonal. Let x of t be the cosine with omega 0 times n0, and x1 be the cosine of omega 0 times n1. So it's just the multiplicator that is changing. And now here I have arbitrary phases for the two of them. You can play then with this script, Control F9. Well, here's one example. I am plotting here just the cosine, not the two parts, the cosine and the j sine. But this extends to the sine as well. If we change the function here, we put sine instead of cosine, we get the same result. So here I have, for instance, n1 and 2, fundamental frequency and the second harmonic. So here we are, x0, x1, both are cosines. In the first case, with x0, I have one period, here I have two periods. Here's the product of them, and I am painting positive parts with blue, negative parts with red. And this third graph shows the integration of this guy, the integration of the product over one period. The period is normalized here. It's going up to 1. So it always oscillates and comes back to 0. Always. Doesn't matter what I choose as n. Let's go 4 and 7 with phase 1 and 2. Very arbitrary phases and multipliers. So it always oscillates and comes back to 0 if the frequencies are not the same. When the frequency is the same, then we get here something minus something plus something. We get 0. E to the 0 is 1. We integrate 1 over a period t0, then we have something different from 0. And that's right, because if I do the inner product of a vector of the basis with itself, I should get something different from 0. If it is an orthonormal basis, I should get 1. If it is not normal, it's just orthogonal, I get something different from 1. So you can play with this as you like. Is there any activity related to this? Yes, there is. I've just remembered it. So, in the end of the day, what should you remember? Then This guy, this set of functions, multiples, exponentials with multiples of some fundamental frequency, they are orthogonal to each other. Proving that they are a basis for every possible signal with this fundamental period or fundamental frequency is a bit trickier, and there are some guys that have fun with it. For instance, une série de Fourier-Lebesgue divergente presque partout. A Fourier series with diverges for almost every instant of time. So with continuous signals, the thing is a bit tricky. If this is really a basis for any signal, any periodical signal, but as electrical engineers, for signals that occur in real life, yes, this is a basis. The exponentials with frequencies which are integer multiples of some fundamental frequency are a basis for any possible periodical signal. But let's check the discrete case. The discrete case is simpler. So you will show that it's a basis. Python activities, exponential vector basis. Use n equals 20. Then you can play with any value you want for big N. Problem 1. Let F, this is a set of vectors. Vectors F index K, with K going from 0 to n minus 1. So you have n vectors Fk. So F0, F1, F2, up to F19. 20 vectors. Let it be a set of n vectors with complex entries. So n vectors, in this case 20 vectors, they also have 20 entries. Each of them has 20 entries. This is really small. Better now. So here I'm representing the vectors as a discrete signal, a function of n. And this is how you compute the vector. E to the j 2 pi. K indicates which vector I'm talking about. K goes from 0 to 19. And n also goes from 0 to 19. And here tells me at which entry of the vector I am in. So K goes here and transports to here, and then n is here. E to the j 2 pi k n. I'm defining a vector of many exponentials varying in time with varying frequencies. And the frequencies are equally distributed from 0 to 2 pi. Verify numerically whether or not F is an orthonormal basis for Cn. A, plot the 20 vectors showcasing the real and imaginary components. So we have to create 20 figures. You do a for loop, it will be a large result, but it will be fast. Is F orthogonal? Explain. How can I check whether this set is orthogonal or not? This set, Fk. Inner products of each combination, they should be 0 when I is different from J, right? When I'm not doing the inner product with the vector itself. So you can do a for loop, 2 for loops, or there's an interesting way of doing this. You create a matrix where each Fk is a column. You create a matrix F, and then you vectorize, you make a very quick set of inner products. You do F Hermitian, which is transposed with conjugate, complex conjugate, F. So if you do this, F is composed by your vectors. When you do the Hermitian, you're transposing it and doing the complex conjugate, and then you're multiplying by this. This equals this line, this column. So entry 0, 0 should be something different from 1. Entry 0, 1 should be 0. This should be 0. This should be 0, 0, 0, 0. Then this should be 0. This should be something not 0. You do this. If this guy is orthogonal, if this set is orthogonal, when you create this matrix and do F Hermitian F, you should get an identity, not identity, a diagonal matrix. Diagonal matrix. If you get a diagonal matrix, then yes, it's orthogonal. How do you see the result? You can do IM show. There's this IM show function. Let me create another code of cell, a cell of code here. Import numpy snp. Let's create some diagonal matrix A. And p.I. I can do plt.em show of A. Please always use color bar when you're using IM show. What's color bar? This. It will indicate the values. But my A is real. Your matrix will be complex. We're interested in, is it 0 or non-zero? We can look at the absolute value of each entry. So there's this function, np.abs, absolute value, element-wise. So we're going to use this. If you get this, then it is orthogonal. If maximum is 1, then it is normalized, meaning that it is orthonormal. If it is both orthogonal and normal, it's orthonormal. I'm asking, is it an orthonormal basis? Those are 3 questions. Is it orthogonal? Is it normal? Is it a basis? How can we tell if this is a basis for Cn. Is it a basis for Cn? Does it span all of Cn? Let's get back to the definitions. Now we're no longer in Cn, we're in R3. One zero zero 0, 1, 0. Does this guy span all of R3? No. If I put one more vector here, maybe. 1, 1, 0. Does it? No. Three, 2, 0. Not yet. If I am non-zero in this dimension, then I cannot use this guy. They should be, if I put this guy 0, 0, something, say 0.2, then it's complete. It's a basis for the I3. Because these three guys are independent. The inner product among them is 0. There are other scenarios where I have a basis with this, for instance, 1, 1.2. I still have a basis. The inner products are not 0 because they're not orthogonal, but they're complete. They can span the whole space. But one case is when the inner product is 0. So I suggest you to start checking whether this guy is orthogonal. You're already doing this here. If it is orthogonal and it has the same number of columns and rows, then it is a basis. If the number of columns is smaller than the number of rows, then it cannot be a basis. If the number of columns is larger, then it might be a basis, but it's impossible that it's orthogonal because it's over complete. But here we're in an n by n matrix. So if it is orthogonal, it's already a basis. But you have to explain it. You can just replicate my explanation. Problem 1. Problem 2, very similar, but now the vectors are the same, f, k, but they're divided by 1 over the square root of n. Why? Probably this guy is not normal and this is normal. So you have to check it. If you do this, if they go to 1, they're normal. If they go to something else, they're not normal. And that's it. This will show you that for discrete signals, if you have a period of n samples, you need n exponentials with n samples to represent anything, any signal that you can put in this period. So the complex exponentials are a basis for any periodical discrete signal. And then in 2 weeks, we're going to do the inner products to find the coefficients. And doing the inner products with complex exponentials means the Fourier transform. If you go to the definition of the Fourier transform, it's just an inner product with an exponential. Here, you have the signal, inner product with an exponential. Then you find the coefficient. Then the coefficient will multiply the exponential to compose the original signal again. But this is a subject for 2 weeks from now.